Okay, good afternoon, everybody. Thanks for sticking it out here as we approach the end of the conference. We know we've had a long couple of days. Thank you very much for joining us today in our session on measuring and modeling air quality emissions. My name is Eric Liu. I'm the Regional Director at Ramboll. We're an environmental and engineering consultancy. And my co-chair, Elena Austin. She's an assistant professor at the University of Washington. We're very excited to have organized a panel of experts here today to present some information on how emissions from airports can be assessed using monitoring modeling and emission estimation tools so that we can better understand how we can evaluate and study air emissions and their potential impact on the surrounding communities. We very much encourage you to submit questions as we go along through Slido. The number again is along on the side of the agenda. So first up, we have Maggie Isied. She's an air quality service manager from Clarity Movement. She has a doctorate in environmental science and engineering from UCLA, Institute of Environment and Sustainability, as well as a master's in public health. She previously worked with the South Coast Air Quality Management District. With her career experience in community engagement, permitting, policy implementation, and in the private sector, she brings to us today a perspective on monitoring technology that can be used to help us understand emissions from airports. Take it away, Maggie.
Awesome. Thank you, Eric. Can everyone hear me okay? Okay. Thank you so much. Again, my name is Maggie, and I'm excited to talk to you today a little bit about monitoring and the work that we're doing at Clarity regarding airports. So Eric really just explained everything, so I can really just give a little bit more context about the work that I do at Clarity. So my current role focuses on using low-cost sensor data to answer project-related questions, and we have recently been getting questions from community groups that live around airports about how they can do their own monitoring and do their own assessment of the impacts of airports on their community. So really excited to talk to you a little bit about our technology and just the work that we do to help projects design networks and how they're using that to do airport monitoring. So just a little bit of monitoring background. So historically, a lot of monitoring has been done at the regulatory or government level. So the map that you see on the left-hand side is showing regulatory monitors only. These are typically run by local air quality agencies like South Coast AQMD. These are US EPA gold standard monitor equipment, so they are very expensive, they are difficult to maintain, and as you can see, there aren't very many of them, versus the map on the right-hand side, which shows regulatory monitors and low-cost sensor technology. So you can see that there is a difference in the density and geographic coverage when you add low-cost sensor monitors in to monitoring platforms, and that really helps us understand the high spatial variability of air quality. So when you're thinking about designing a low-cost sensor network, there's a lot of variables to consider. So this is actually part of my dissertation work at UCLA, is how different groups, whether you're a community-based organization all the way up to a government, can think about designing a low-cost sensor network. So the way to use a tool like this is in the center of the circle is really the three main goals that we have. So first you want to establish the project goals. So for example, in the case of airport monitoring, maybe your goal is to understand the impacts from the airport on a local community. The second step is to identify the study area, how far out do you want to go from that airport? And then finally, you want to use all of the variables on the outside of the circle to determine the number, type, and location of the sensors. So all of the variables here are extremely important, but in particular for airport monitoring, the big one that's important is the pollutants of interest. So a lot of low-cost sensor monitoring is very focused on PM 2.5, which is one of many pollutants that are emitted from airports, which I'll talk about on the next slide. But there are other variables to consider when you think about monitoring, particularly around airports. One is location feasibility. So do you have access to the site that you want to monitor? Is it a residence or a school? And who do you need to get permission to do that monitoring? Budget is also a big one. Whether you're a government agency, a nonprofit, it is important to identify what your budget is, and that's going to help you determine not only how many monitors you can buy, but what pollutants you can actually measure. And then at the top right, you can see that there's like computer and spatial modeling tools that you can run that use a combination of land use regression and historic air quality data to pinpoint exactly where monitors should go. So there are a lot of tools out there to assist with placement of sensor network, but there are essentially quantitative and qualitative variables that should be considered when you're thinking about setting up a sensor network. So when we're thinking about airports, it's important to identify what the sources of the air pollution are from these airports. So the most obvious one to everyone is probably aircraft, but when we're thinking about air quality as a whole, we also want to think about vehicular traffic, whether that's passenger vehicles coming in or any ground support equipment. We also want to think about any transportation coming, like again, on the runway and externally. And then you also want to think about any APUs, ground, basically any type of units that are going to emit air quality, or air pollution, I should say. And on the right-hand side, you can see that there is a long list of pollutants found at airports. And so beyond the typical pollutants that are measured by low-cost sensors like PM2.5 and NO2, you also have black carbon, carbon monoxide, ultrafine particles, VOCs, and hydrocarbons. And so identifying what pollutant you're most interested in is going to be the most critical step for identifying what monitoring equipment you can buy. So the company I work for is called Clarity, and one thing that we really work hard to do is make sure that monitoring technology is accessible and easy to deploy. So one other thing to think about when you're thinking about setting up a network is to make sure that the monitors are easy to deploy, you don't have to get a lot of permission to install them, etc. So Clarity, for example, our bread and butter monitors both PM and NO2. It's cellular and solar powered, so it can be hung anywhere, as you can see in the pictures on the right-hand side. They're really easy to deploy, and so these are really important when, again, when you're thinking about is a community going to put these up, is a government going to put these up, you know, making sure that it's easy for them to do. And then thinking even beyond just the monitor itself, we've also thought about adding additional pollutants that are kind of more like newer now, I would say, in the low-cost sensor space to monitor. So as I mentioned on the previous slide, there is a very long list of pollutants that even Clarity doesn't cover that are being emitted from airports. So some other things that we also include in our kind of platform are wind modules. So it's important to understand wind speed, wind direction, temperature, and relative humidity when you're talking about air quality. You want to know where it's coming from, you want to know where it's traveling to, et cetera. And then again, thinking about pollutants like ozone and black carbon are also important, because relying on PM2.5 when you might need to be monitoring black carbon is an important factor to consider. And so thinking beyond monitoring, this slide really just shows a list of all the different variables to think about in human exposure to aircraft emissions. And this is going to be important, again, when you're trying to determine what monitoring you want to use. So for example, if you're looking at the occupational health and safety of people actually working at the airport, you might not want a regulatory monitor, you might not even want a low-cost sensor, you might need a personal monitor. So again, these are just all the different variables that need to be considered when you're trying to think about how to monitor airport emissions. And then just want to finish off with some pros and cons of using low-cost air monitors for airports. So as I mentioned earlier, this really increases accessibility to non-air quality experts. So having technology like Clarity allows community-based organizations to take matters into their own hands and really understand their air quality. The second one, as the name implies, low cost, they are absolutely more affordable than regulatory monitors, which can run in the tens of thousands of dollars range. Low cost sensors run anywhere from in the hundreds to 10,000 range. So they're definitely a lot more accessible, and again, can allow for more spatial density, which is kind of the third pro of using low cost sensors. You can increase the density of your monitoring to see if there's any type of air quality gradient, right? Like maybe you set one up 100 meters away, 200 meters, 500 meters, and you can use that to measure, how far out we're seeing the impacts, are we seeing them at the fence line, things like that. There are a lot of cons still for using low-cost sensors. So the main one is pollutant types at airports. So as I mentioned previously, there is a laundry list of pollutants that are emitted, and not all low-cost sensors can measure all of those pollutants. So we wouldn't want to set up any organizations for a disadvantage. So it's important to be very clear about what that technology is able to measure at this time and what it's not. because although a community may be concerned about what's being emitted at the airport, they might not be using the right technology to measure it. The second, which is a big challenge in the low-cost sensor space, is accuracy of data. So because these are lower cost, they do break more easily, their lifespan is a lot shorter, and so it's really important to make sure that they're being maintained properly. In addition, it's also important to make sure they're properly calibrated, so the device is with a reference monitor for a while and then is basically calibrated up against that device to make sure you're getting the most accurate data possible. So again, there's a big discrepancy now, and you know, this is very much a concern in this space about how accurate the data is, but with pollutants like PM 2.5 and NO2, there's a lot of work and a lot more certainty in how well low-cost sensors are performing, which is good. The third con is access to certain locations. So again, going back to the community example, if a community is like, I want to monitor right here next to the airport, if they don't have maybe like an agreement with the city or with the county or with the airport to do that, they might need to find another solution. So you might want to monitor somewhere, but if you don't have the access to that location to do so, you won't be able to. So it's important when you're designing a sensor network to say, like, do I have access to the location where I want to do the monitoring? And finally, the last one is balancing community concerns with resources available. I think all communities would love to monitor all the pollutants listed, but on a low-cost sensor budget, it's just not feasible to do that. And in fact, there isn't a lot of monitoring for all those pollutants listed that's reliable today, although it is a technology that is emerging. So I think it's important to make sure that we're balancing like what the community concerns are and prioritizing those when moving forward in establishing project goals for doing monitoring. And that's all I have. Thank you so much. Questions at the end, right?
Yeah, and I'll invite all of you to submit questions to the Slido, and at the end, we will be going through questions for all our speakers.
Great, thank you very much, Maggie. Next up, we have Gwen Pelletier. She's an principal environmental scientist with CDM Smith. She's been working as an air quality specialist for over 25 years, and she's a long-term member of the FAA's user group for AEDT, where she assists with beta testing of model sprints and revisions. With this expertise, she will be sharing with us how the AEDT model helps us understand air quality emissions from airports and aircraft. Please welcome Gwen. Thank you.
Thank you, everyone. So Eric just gave a great discussion of me, so I won't spend much more time talking about it. But I'm going to give a brief presentation about how you can use the Aviation Environmental Design tool to do an airport air quality analysis. And so AEDT is a tool. If anyone was in the environmental justice session last night, you would have heard a brief overview of it. But it is a model that can be used to estimate both air quality and noise. And so today I'm going to talk about kind of a brief high-level technical overview of what AEDT is, what its benefits and limitations are, as well as some new features in the current version of AEDT and what the next steps are in future development. So this is somewhat of a busy slide, but I kind of did that on purpose so you kind of understand how complex AEDT is. But at its core, it is a database management system. It runs on Microsoft SQL Server. And so it has a series of built-in databases that contain information on both the airports themselves, as well as your emission sources, such as your aircraft, your ground support equipment, anything else. So when you're building a study, you're going to pull all these databases in, and then you're going to build what it actually is you're studying. And then AEDT is going to do its thing. From an air quality standpoint, it does a kind of interesting thing where it's a space and time model. And so it uses what's called a voxel grid. And what that means is it builds a huge kind of cuboid structure over your study area. And as your aircraft are flying in, every single time it hits one of those smaller cuboids, it's going to assign emissions to that cube. And so when you do the next step, which is dispersion, to look at your concentrations on the ground, it takes all that information about where in space the emissions occurred, as well as the time it occurs. So there are a lot of different emission sources at an airport. There's a couple things that AEDT can calculate internally, and that includes the aircraft themselves, the ground support equipment, which is anything that's kind of running around on the tarmac to kind of support the aircraft, and auxiliary power units, which are kind of small onboard engines that kind of help the aircraft operate the lights and air conditioning and other things while it's at a gate. It can also estimate emissions from stationary sources, such as maybe a boiler or a central utility plant to power the terminals, and then area sources such as a fuel farm. What it cannot do internally is look at ground access vehicles, which is any motor vehicle coming in and out of the airport, such as shuttles, buses, passengers, or construction sources. However, you can use the EPA's MOVES model to estimate emissions from those sources, which can then be imported into AEDT. So I keep talking about what is emissions inventory, and so I do want to spend a brief amount of time talking about what exactly is going into the model to actually estimate your emissions from aircraft. And it's a lot of data. But first and foremost, the most important thing, at least from an air quality standpoint or is aircraft standpoint, is the actual fleet mix. And so you're actually telling the model the exact airframe and engine combination that you're flying. Assuming it's within your database. You're also going to look at the number of operations, how the aircraft is flying, and also how it's moving around on the ground. And then also it's going to pull your non-aircraft sources. So there's a bunch of different emission pollutants, that's what I'm looking for, that can be estimated emissions inventory. So it looks at both your criteria air pollutants and precursors. So these are pollutants that generally have some sort of ambient air quality standard to regulate health effects. It looks at greenhouse gases, speciated organic compounds like toxics, and then some other pollutants. So what is its benefits? The main thing is it is a comprehensive modeling system. It really does look at the whole picture. Before AEDT, you used to look at your emissions separately in a model called EDMS, and your noise separately in a model called INM. And so AEDT kind of merges everything together into one model to look at the big picture. It also considers various environmental effects, changes in the aircraft weight or how it's performing, meteorological data is all taken into consideration. And then, as I've said a few times before, it also looks at all the major sources of pollution at the airport. AEDT helps with environmental review. If anyone is familiar with the laws called CEQA in California or NEPA, these are requirements to actually look at the environmental impacts of a project at an airport. And so AEDT can help you look at what the impacts of your project are, as well as any alternatives, and if you're compliant with the different regulations. This was also mentioned briefly yesterday, but it does have some modules in it to look at both nearby environmental justice communities, as well as communities that might have limited English proficiency. And so it does help with communication and outreach. And because of this, it allows for informed decision-making from both the airport and any stakeholders and the community. So I do want to talk about some new features in AEDT 3F. One thing that may not sound interesting on kind of the outset, but actually is pretty important from a community standpoint, is when you're doing an emissions dispersion study, you're actually there's things called source groups. You're kind of lumping different emission sources into these source groups. And so it used to be you could only look at aircraft as aircraft. But now, with the current release, you can actually separate out your piston engines from your turbine engines. And this is extremely important because it's those piston engines that have your lead emissions. And so this just makes it a lot easier to be able to understand your lead emissions and actually look at it without doing a bunch of other calculations. It also expanded the greenhouse gas calculations. AEDT has always had greenhouse gases in it, but is always limited to mainly carbon dioxide and water. So of the current release, they added methane emissions. It does not look at nitrous oxide, and that's mainly because it's so negligible in aviation, it's kind of a non-issue. It does use the current global warming potential for methane. You cannot change that within AEDT, but at least it's transparent, so you know what it's using. And also, because it changed some of the technical methods of estimating greenhouse gases, it kind of had some ripple effects to other pollutants. And it's just because the way you calculated things changed, and so therefore some of the emission indices for other pollutants have got updated. Another thing it can do, and actually Kevin Lane's going to talk about this a bit more, is it can look at non-volatile particulate matter, or UFPs. So now it can actually estimate the mass and the count of UFPs. However, while it can give you this data, we don't really know what the health effects are. They're currently under research, and there are no thresholds for it. But at least we're kind of moving in a direction to look at it further. And so, what are limitations? We just heard Maggie give a great speech on monitoring, and it's very important to understand that modeling does not replace monitoring data. You're looking at a theoretical model of just like your airport itself. And so you're not capturing real world emissions, such as a nearby freeway or other emission sources industry. And so it's possible that your modeled results may not replicate your monitored results. So it's just kind of important to keep that in mind. There is a lot of data requirements. And so because there's so many different ways you can put in data or analyze it, these like kind of slight tweaks might cause what I call like fuzziness. There might just be slight variations in your inventory, depending on how the data is input. There's a lot of unknowns. Often we have to take, say, like a daily flight schedule and somehow turn that into annual emissions. And so one technique is to use these operational profiles, which is using historic information from an airport and kind of scaling it up to annual emissions. And so there's a lot of variabilities in that, and so it does make the data a little bit less precise. The assumptions you put into it are static. Again, you're looking at a database and you're saying, I'm flying this aircraft so many times at this time of day. And so because it's kind of a static picture, there might be some slight differences in the real world. There also could be unknown variables, something like the grounding of the 737 MAX, that may not be captured by your model if you assume those aircraft are operating. While it's a complex model, it is still simplified in the fact that you're basically looking at emission factors. It may not take into account some real world complexities. You might be having to take data from, say, another model like SimOD, which is an airfield simulation model, and somehow interpret that as AEDT. So that, again, is just one more kind of layer that could add some difficulty. And then just the concept of data overloads. It's like there is a lot of data out there now. So understanding like what data to actually use and how to simplify it and how to bring the model is one thing to consider. So what are the next steps? I do not want to spend a lot of time on this slide, but just want to kind of highlight that AEDT is constantly evolving, and so they're constantly pulling in research to update both the air quality and the noise impacts. One thing that AEDT does not currently do is actually lead emissions. Although I just gave a slide about how you can now separate piston engines, you'd have to use like another way to actually estimate the actual lead emissions. And so AEDT is currently working on a module that actually allows lead emissions to be modeled. The FAA actually has it currently as like an alpha, but should be available for public release in the next couple of iterations of AEDT. And so this is my quick overview of AEDT. I know we're holding questions till the end, and so look forward to hearing from you later. Thank you.
Thank you very much, Gwen. Next up, we have Kevin Lane, who's an assistant professor at Boston University School of Public Health. Dr. Lane is also a principal investigator for the Federal Aviation Administration Ascent Project 18 Community Measurements of Aviation Emissions Contribution to Ambient Air Quality. Quite a mouthful. With all of this knowledge of the intersection of air pollution, built environment, urbanization, and his expertise in big data and spatial research, we're very excited for him here to share with us how his work is going to help us better understand how communities are impacted by the air emissions from airports and other surrounding sources. Take it away, Kevin.
Thanks a lot, Eric and Elena, for the invitation to be here. And thank you for those that are in the conference room, as well as those that are online that are listening today. And yes, I do have the longest titles ever, I think, in my department for research studies. But really, it really is a pleasure to be able to share some of the work that our team in Boston has been doing around monitoring and modeling of ultrafine particles in communities near the Logan Airport, and also to provide a longer sort of view on where's the state of the science in regard to ultrafine particle studies from a Boston perspective, where we've been studying, I've been fortunate to study ultrafine particle health effects for about 15 years in Boston. So we've been doing a lot of this work, and it's a lot of unique lessons that we can share and learn. And there's already been a couple great presentations that have talked about ultrafine particles already. Yesterday, talking about brain cancer and respiratory cancer relationships and associations. So for those that might not have attended that, I'll just also start off with the basics that we're all on the same page. When we're talking about ultrafine particles, as Gwen was saying, that can be in the non-volatile PM phase as well. I think this community, as well as others, when we say particulate matter causes adverse health effects, it's well understood. When it's talking about ultrafine particles, especially particles that could be potentially down in that volatile to non-volatile shift that's occurring in the nucleation phase, we know very little in terms of the health impacts overall. So this is, I think, one of those areas where we need more research. And when we're talking about UFP, we're talking about less than 100 nanometers, and most of the health studies have focused on that, a total look at ultrafine particles, and just now we're starting to get into size distribution, which I'm not going to be presenting on those results today, but I will be sharing some of the work we've done on total PNC. And that's also a unique piece, because we're thinking about how we could potentially think about future emissions standards and or national ambient air quality standards. We're thinking about EPA, what the health studies are really focused on particle number concentration. The mass is really contributed, especially in those smaller sizes, really negligibly to a mass-based metric on PM 2.5. So it would require a different type of thinking, but it also creates some unique challenges when we want to do monitoring as well as health studies as well. Let's see. There we go. Just provide a little bit of background. Ultrafine particles, they typically, the byproducts of combustion, large reactive surface, are believed to be more cytotoxic than their larger particles. There's also limited lung and systematic removal that can occur. The particles have been so small, we heard yesterday, and I'll just reiterate it, the mechanism of action by which we think that elicits adverse health impacts is through an inflammatory response that can occur both in terms of in the localized respiratory area, increase in cytokine, C-reactive protein, but also has been shown to go and translocate past the endothelial line of the alveolar region and transport across the systemic circulatory system, deposited in different organs throughout the entire body, eliciting systemic inflammatory responses. And that's some of the work that has been going on with my group as well as others, and especially in the European groups have been leading on some of these areas as well. In terms of epidemiological evidence, until about 10 years ago, it was really minimal in terms of looking at a lot of health studies. And even today, if you look at that, the EPA's ISAS reports that have been coming out, including the most recent one, is sort of saying that there's just not enough health evidence to support the promulgation of a new ultrafine particle standard at this time. Really, the CASAC, when they did their review, were saying that there could be cognitive impacts that could be more potentially on the pathway as suggestive. But when it comes to cardiovascular and respiratory related research, there's a lot of mixed results. There's consistent positive associations on the cardiovascular. On the respiratory side, it's actually quite mixed. And some of that can be due to what exactly the EPA has been saying, and we need more of, which is improved exposure monitoring, exposure assessment techniques, and more health studies overall. Oops, sorry. think about too many. In terms of source attribution, what do we know? We actually know a lot more about this than we do on the health impacts. There's spatiotemporal variability. A lot of studies showing anywhere between 9 to 12 kilometers or a little bit further away, being able to measure ultrafine particles from aviation sources. Mobile sources being a little bit more closely impacted to the localized region in the exposures. In addition to mobile sources, we know, especially if you're going to do monitoring, and you have to go beyond just roads now, you have to think about restaurant-based exposures, wood burning, as well as construction operations that could be potentially impacting those results. And a key challenge that was just mentioned in both of the projects, the presentations, challenges in developing models for this. Monitoring is not going to be always outlaid by models, but even our models right now are imprecise and can't really fully generate between roadway and aviation. That's what we're moving forward towards. The Move Up group from Elena, our work, as well as in groups in Europe, we're trying to get at the different source-specific models. But overall, exposure assessment from these models also needs to be improved as well. I keep on hitting the wrong button, my fault. So I'm just going to take a slight quick deviation into talking about traffic so it can help us better understand some of the limitations of exposure and health impacts. And this is from work that was done between 2010 and come recently and was led by Doug Brugge at Tufts University and John Durant as well. And now Doug is at UConn and still is doing community-based participatory research study. I did my entire dissertation on this work as well for my PhD and continued in this area. And I have hyperlinks to anything that's in here so you can get right to the slides. Two quick things I want to come out from this study that we've shown, and then also people like Gerard Hoek and others in Europe have really been hitting on, is if we want to do health studies related to this, and I'm focused on roadways, because that's where the vast majority of the health impact and exposure assessment research has been done, is that we got to know where people are. One of the key things that we found in roadway research is that if we want to see associations, these are highly spatiotemporal exposures people are receiving in peak levels at high concentrations, and then when the roads are reduced in traffic, they're not there. We actually found in our study that by collecting time activity information, applying it on hourly levels to our models, it improved our overall assessment. The top box on the right shows you sort of a business as usual residential exposure that's typical of PM 2.5, which works beautifully because PM 2.5 doesn't have as much spatial as it might have spatial variation that's going to occur. But with UFP, you're 250 meters away from the road, and if you're working during rush hour traffic, you're not exposed during those time periods. And the bottom actually shows the differential in this. Additionally, for those that have worked in geocoding or community projects, geocoding is really important. I've published a number of papers on the importance of geocoding and some of the inherent problems. This is an example of how community-based participatory research enhance epidemiological health studies. By working with our community partners in the Chinatown area and Somerville as well, we're able to pull out public housing. Many cities, similar to Boston, put their public housing right up against major roadways and other high exposure areas. A lot of centralized public housing, especially in Massachusetts, has single site address locations. That's not where the people live, right? In most of our public housing, there are multiple blocks, so you would have a lot of misclassification. We refer to this as exposure misclassification in health study, and the reason why I'm bringing up both of these is because if you're thinking about in the future planning to get into a health study, we're seeing not just here, but in other studies in Europe, it's really important. Even if you're just talking about roadway, this could be the difference potentially between seeing associations or not in ultrafine particle-based research. The graph on the left actually shows a relationship between a residential exposure to ultrafine particles measured as particle number concentration, its impact on C-reactive protein, which is a measure that would be a cardiovascular subclinical measure. And we actually see that there's no actual significant association when we do that. When we apply time activity through community-based help-in on this and collection of the data, we actually see a linear association overall. We've published a dozen papers, some with and without the time activity. When we use time activity, we actually see associations. When we don't, we don't. This could have some other proliferations in the field as well. So when you're looking at ultrafine particle health research, you want to consider these as a key element. And we know that's going to be important for aviation. Roads, we have a clear distinction time period, especially in areas. High traffic, low traffic of when we can identify people. Aviation, it's not as clearly timed always. It's timed, especially in a complex airport like Logan Airport, where you can have some of the different LTO and different configurations of patterns be very different. So when it comes to community measurements of aviation emissions, that's our Ascent-based project. What we've been doing is starting in 2020, collecting ultrafine particle data along each one of the major LTO arrival or departure pathways where we can get into and collect multiple years of ultrafine particle, NO2, and other data sets as well. We're doing both stationary monitoring. We're using condensation particle counters as well as some size distribution using TSI's FMPS as well. We'll also have a mobile monitoring plan. That's the electric vehicle that you see in the bottom left with Tufts University, collecting a lot of data. The Move Up study, many other groups in Europe are using this sort of combined approach. A new thing we're piloting now is UAS, so we can get at vertical dispersion patterns. Roads are pretty simple. You get the perpendicular with a little bit of dispersion, but we need to be able to start doing some plume chasing to help improve sort of that algorithm related to the dispersion characteristics of in-flight contributions, which is really our study question, is to quantify that in-flight and ground-based flight contributions in these communities while pulling out what would be that traffic piece overall, so we could distinguish between the two. Before we started the project, there was some initial studies that were more shorter term by Noakshi Huda, who's now a part of our team with John Durant, showing the relative importance of wind direction, wind speed, hour of day, and the diurnal patterns. So this is sort of proof of concept aspects of where we were monitoring already and how important it was. If you're thinking, and you heard me say you started in 2020, what's the big issue? The COVID pandemic. So we actually wrote a scope of work that wasn't designed to deal with the pandemic, but we actually took advantage. I think, understanding climate and air pollution impacts is one of the things that actually comes out of this pandemic that hopefully will be the only one in our lives that we can actually do a natural experiment with. Both the cars were taken off the roads, like you can see in the example here by Huda et al. In 2020, which is examining the first few months where the state of emergency was put in place, with the dip down in different types of modes of transportation by 50 or 60%, and there being a corresponding PNC relationship. University of Washington published a similar paper, Steve Larson, that does a longer time trend on the road UFP. We've published 2 years ago, as my doctoral student, Sean Muller published one of his dissertation papers, which is examine a multi-year comparison at 18 months of the COVID-19 as a natural experiment to examine ultrafine particles impact pre-pandemic, during the state of emergency, and after 1 year later. And what you see here is a time series. Because we've had a number of different studies, the red line indicates the PNC difference from background, which would be the pre-pandemic time period. But the red line indicates the intermittent phase. Even with a study in Boston where we've been collecting ultrafine particles, we'd have about 10 years of continuous data. It's really difficult. Again, it really speaks to the importance of having long-term sites near sources so that we can get an understanding. We ran out, as soon as our study started in March, we sprinted right out and got the monitors up and running so we could collect this data. We've been collecting it through 2023. So we've captured the entire change forward overall in time. And what we actually see in the bottom line there is the pre-pandemic time period, the state of emergency when roads dipped down to approximately around 50, 60% and started coming back. And then, but aviation at that time was well below 20%. In the 2021 time period, it only came up to approximately around 60% its return. It didn't really return until almost the summer of 2022, back to like close, approximately 100%. We have continued this analysis out to be able to see the differences overall. What we observed, if you look carefully at our wind-rose pollution plots, is that that cone, which would be our impact sector when planes would potentially be impacting the community in that area, you see that really high level. When the roads and the aviation are removed, you see a rapid reduction in both. Interestingly, when roads are coming back, the aviation is still minimal. To the mean of what we're seeing, the mean and median, it's pretty stable. That tells us a lot about peak exposures from aviation and what's contributing. Roads could be aiming towards what is the mean, which means that the health studies that are focused on annual average mean might also be missing the aviation. So we're actually starting to look at peak-based models as well, which turns me to, one second, just a quick summary on this one. The PNC levels that we actually saw during COVID reduced by 50%. In urban background areas, we typically see between 60 and 80,000 that can be occurring in Boston. In some of our outlying suburban areas, it can go as low as 3,000 or 4,000 particles per cubic centimeter. So we expected to still see some, even if the roads and planes were gone. PNC levels reduced largely in the impact sector, but not in the other area as roads came back. And during the late SOE, the mean PNC remained lower. Why is this important? Natural experiments can really be ideal to show this. This is one study, a couple others are starting to look at this impact as well on long-term trajectories. One final thing I just want to share is our spatial temporal regression models in one of our most recent papers, where what we've done is along the arrival path that's most commonly used into Logan Airport, we collected data in 2017 by my chair, John Levy, when he was running the study before I took over, is being able to develop spatiotemporal regression models for this. And we were able to build a robust model at the mean and the 95th percentile to see the differences. We actually saw stronger associations when we're examining PNC at the 95th for our flight activity measures overall. And what you're seeing here is when the arrival aircrafts are over 30 per hour, so high frequency of flights coming in, there was a significant increase in our sites N1, N2, and I1 that you see here in the corresponding map. What we actually saw is that in the first one, there was 11,000 particle increase during that time period compared to when there was no flights. There was approximately a 9,000 in the I1, and then the N2 site, there was approximately 6,500, indicating that's the arrival extra contribution to the communities when there's an exposure. But again, this actually represents in our study only a time period of 20% of the time. So most of the time people have low exposures, which means if we aim a health study the way that it's currently being done for PM 2.5, other air pollutants at a mean and or other exposures, it might not match up. We're looking at higher exposures in those peak ranges, and hearing a lot about the noise has really started to make me feel a little more confident, like these are peak exposures under specific time periods of impact. Overall, what we found is really important is that we can model the contributions and quantify them at the mean and at higher exposures, and we're now starting to use machine learning to improve our models. These models range between approximately R-squares of 0.42 and 0.56. Our new machine learning models are substantially more robust overall, but they're seeming to come within each other's confidence intervals for accuracy. In terms of summary, contributions to aircraft UFP, really complex overall. We need more research. Health studies need to account for multiple sources, so not just the unique properties around exposure assignment need to be taken into consideration, like time activity, but also similarly noise, other factors, other air pollutants as well. And current approaches to assign exposure to these air pollution health impacts might not be sufficient at this time either. I just want to thank my project team of Boston University, as well as Tufts University and various doctoral students currently and past, and also just thank my funders, which is the Ascent FAA Center for Excellence, Alternative Jet Fuels and Environment, Project 18. If you want to follow up with me, you can reach me at my email. It's quite simple, klane@bu.edu. Thanks.
Thanks to all our presenters for, okay, we have all our presenters still. Thanks for great presentations. I'll be asking some of the questions that have come in, but as you reflect, especially on the last presentation, you haven't had as much time, please feel free to send those questions in as well. I'll start with a first question from Denny Schneider. It was for our first presenter, Maggie, but I think I'll open it up to all our presenters, which is some thoughts on why, if there's not a strong correlation between PM 2.5 and ultrafines, why do we not have more monitoring for ultrafines currently?
I can attempt to take a stab at this question. So I think I can reflect a little bit on my regulatory experience for this one. I mean, ultrafines are not a criteria air pollutant, and so there isn't, you know, by the Clean Air Act, there isn't a lot of investment in monitoring for them. So right now, that's really where it stands. And I think PM 2.5 is the kind of the conduit and the need for some more of this monitoring, and really the need, as you know, as our presenters mentioned, about focusing on ultrafine. So I don't know if anyone wants to add. Kevin?
Yeah, thanks, Maggie. I'll just add another one. What we're actually seeing when it comes to ultrafine particles is the best monitoring strategy, if you want to understand what the full spatial temporal exposure is of your community, is to have mobile. So it's trying to think outside the box as well in terms of going beyond just stationary, and not to say that you have to have a full-time mobile. There's been research showing that you need, you know, just a certain amount of data collected across different seasons to be able to robustly understand what is that different exposure levels. So I think it's not just thinking like if the monitoring sites that we currently have in stationary are inadequate or do we need a lot more. Because another key thing is the low-cost sensor technology, as Maggie's saying, it's still under development for UFP, and these equipment are quite expensive and require a large infrastructure to maintain.
Thanks a lot. I think we'll move on to a question for Gwen. And it's related to some of the presentation and comments you made around climate change. And this is a question from Debbie Wagner asking if, or asking about the NOx emissions from jets and its potential contribution to climate change. And so is there opportunity to include NOx in the AEDT model, and what might be some barriers to doing that?
Oh, NOx is, nitrous oxide into
It was nitrous oxide, yeah.
Yeah, nitrous oxide is just a very, very, very small component of aviation. And so while ADT does not analyze it, there are ways you can look at it. And so I've actually done calculations kind of, off the model to look at some emission factors. And so you can look at it if you want to. I don't believe the FAA is interested in including it. Maybe they will in the future, just because it's relatively small compared to the impact that CO2 and methane has.
Thank you. We'll do a next question for Kevin, and it may be difficult to answer briefly, but you can do your best. As from Allison Kerr, how do you distinguish the road emissions and jet and aviation emissions in your studies?
Oh, I love this question. I should actually ask Elena to answer it because one of her students, like in postdocs, did a paper on this. In terms of the way that we approached it when we had total PNC, I'll answer it that way first. And Elena, cut me off if I go too long. The idea is that we actually did fit for purpose monitoring. Since we know that if we want to get roads, a lot of our sites were designed and specifically chosen to be more than 250 or 300 meters away from roads. So we can almost entirely rule out that in our case, we're doing that. That would mean if you want to do a health study, you would have to have two different models. You'd have to have one developed for roads and one for aviation. Just what happens in Boston, we have a 15-year road model so that we're able to do some of that work. And some other cities have been doing ultrafine particles as well with aviation, and roads could do similar things. The way that we're also thinking about this when we're talking about total is also thinking about size distribution. One of Elena's papers that came out of the Move Up study, and then more research that's being done in Europe, is starting to use the size distribution. When you're getting down into the less than 20 nanometers, you're getting into that nucleation phase, coagulation, before you get into the aggregation. I mean, what you're really seeing is particles that have to have really, really close to the engine and also highly coming out from that. Your paper, I believe, was showing relationships stronger with the aircraft at the smaller end and then the higher.
Yeah, and I can give a brief thought on this, which is really there's no one marker that distinguishes roadway and traffic. And so it's very important to have multi-pollutant measures, either in the size distribution or including black carbon and gaseous pollutants, to be able to look at the ratios and relate those back to emission factors for the sources of concern. My perspective, if anyone was asking. Okay, I think we will have a question now for Maggie, if I can find it here, which is maybe an adaptive question, but briefly, do you have some guidance for communities if they're interested in identifying how many nodes they would need to use to monitor for aircraft or roadway pollution, and some thoughts on how to select those sites?
I love this question because this is what my dissertation focused on. And I wish I could give a very clear answer of the number, but as I showed in my presentation, it is a very iterative process to come up with that. And so I think using that decision framework and walking through, what your project goals are, which in this case would be to, evaluate impacts from roadways and airports. That's an important question. And then potentially identifying what your budget is and where you can monitor is going to be really important. Without more information, I can't really give more than that, but I think those are the key variables to start with to identify locations. And then for community monitoring, it is also really important that you either have some agreement with your local municipality, whether that's city or county, or whether you have a contact there or somebody who's going to allow you to assist in citing locations for monitoring. So that's going to be critical. Yeah, every project puts different weight on different variables. So yeah, I hope that's a helpful start.
And maybe one short follow-up, which is in the case of aircraft-related emissions, have you thought, or do you have any suggestions for how to think about the altitude of the deployment of the sensor?
Yeah, so in our experience right now, we haven't done like a very technical analysis, mainly because a lot of the groups who've talked to us are weighing the science of where they should go versus where the community wants these monitors to go. So, if the science tells us, or the science is telling them, like a lot of them are looking at meteorology patterns, wind speed, wind direction, might tell them to place it somewhere where people are not located, and that's not what the community wants. So again, it's a pretty iterative process and very project dependent. For some communities, what we've suggested is if they are able to get one as close to the fence line as possible and then push it back by 100 meters all the way out to about a mile. And again, that's very arbitrary based on budget and all these other variables. But I think the key here is making sure that the weight of what the community wants is aligned with what the science says, and they're not always the same.
Thank you. I think we'll go to Gwen. There's a couple of questions that are a little bit related and probably driven by our topic today. So the questions are about the AEDT model and where the data comes from for the ultrafine, in particular the ultrafine particle estimates, and how those are related to the NVPM estimates in the models.
And actually, Kevin might be able to speak to this as well. And I kind of briefly mentioned on like the ascent studies, and so there are a lot of studies out there and research that's being done on UFPs, and so that's kind of where a lot of the data is coming from. There is some different like calculation methodologies that actually just got updated in AEDT 3F that will estimate UFPs, and so it's just an iterative process. I mean, the research for UFPs is relatively new, as we've already said, and so it's just a matter of kind of refining the equations and the methodology, and continuing to do research and monitoring data and kind of understanding how UFPs are being done, and then AEDT will get updated as more knowledge is known. So I apologize. I realize it's kind of vague, but it's so new that it's kind of hard to.
Yeah, and I'll let Kevin take us.
Yeah, I'll just briefly add, that's actually one of the underpinnings we were talking earlier of our work. It's not just to understand what's happening here at Boston. That's why we need more monitoring data, and we need them at, different airports under different conditions as well, because the idea is, since it is so specific locally to what's going on conditionally, we need and airports are really different. The LAX LTO patterns are extremely different from Boston, so we need to be able to understand and have enough data so that the models can be done. That way, we could do this other work at other airports, but not potentially have to monitor at everyone. It's already really long-term and difficult to do, so our project is actually feeding data to people that are trying to improve the algorithms.
And I guess I'll ask you a question that might put you on the spot a little bit, but how, in both of your opinions, how reliable and accurate is the ultrafine particle emissions data, but also the dispersion data within the
Yeah, I think for UFPs, that's probably a question for Kevin. I mean, dispersion, it is very conservative. It's called a Gaussian plume, which you're kind of assuming this kind of steady plume, but it is conservative, and so if anything, you might be overestimating impacts. The FAA is actually working on a whole new way to disperse pollutants, and so they're, instead of using air mod, which is the model that's used now for dispersion, they are looking at creating something new, and so just to kind of improve, the math. Air mod, it actually is already making some improvements to estimate aircraft emissions. I didn't talk about my presentation, but there is, the current version of air mod actually looks at the plume rise. So basically how heats kind of affect dispersion. And so it is ongoing. But I mean, it's a model. And so like it'll never match Maggie's data, but it does the best it can. Like it probably overestimates more than anything.
Thoughts? Okay, great. Thank you. Kevin, there's a clarification. Bonira Kai asks, how far away were the monitors from the center of the airport in the study that you presented? And have you had discussions about monitoring at the airport or at the fence line? I added the fence line.
Yeah, no, and yeah, it should have been clear. The study that was done in 2017 by John Levy, and I was actually still just a postdoc at the time on that one. It was really interesting because there hadn't been as much done on arrival. That one, we actually got further away. Our sites were, every site was at least 2 kilometers, and then we, I think, maxed out at around 12 kilometers away from the airport overall. And in our furthest sites away, but we also had different distances from the arrival path 4L4R, which is the most widely used one coming into Logan Airport for arrivals. So we actually were trying to look at both the distance from the airport, but also distance from the arrival path as being a differential. That's why you actually see in our near sites, one of the intermediates is actually has a higher, because it's a little bit closer to the arrival than it is the airports. So there's some interesting further analysis we need to do that. The other study that's trying to look at specifically what's in closer proximity on the quantification piece are sites that are furthest away are in Revere, and I believe they're just around like 6 kilometers away. And that was influenced based upon our study that we've done on the arrival to better understand. We want to really get good at quantifying in those near exposed communities, the differentials. The last question about a near site monitor, that's a different question since our scope of work in the past has been about what's going on in the community specifically. We are now collecting some data that's closer on the airport site.
Thank you. And we only have a couple minutes left, so I think I'll ask a broad question from all of you, and I apologize for the questions we didn't get to today. And that question is, a lot of people in our audience are community members and port operators, and if you can think from your perspectives on some next steps that they might consider with respect to the topics that you presented today in addressing some of these questions.
Yeah, I guess as far as next steps, I think a lot of my work is NEPA, which is actually environmental impact reviews. And so I think when it comes to the community, I think next steps is to improve communication with the community, because the AEDT does have a lot of tools to make sure you're looking at disenfranchised or limited English-speaking communities, make sure you do produce things that's appropriate for them. And then also it's not really a modeling issue, but then also just kind of working with them from the beginning to make sure they kind of understand, the project and what you're doing and, the pros and cons of the analysis.
Thank you. And thank you for going first with that question.
Take the next stab at this. I think for communities, it's important to also understand that even with the best modeling and monitoring data, you might not be able to get the answer that you're looking for right away. Like, I think there's an iterative process here with how frequently airports are changing and, adapting their technologies and their methods. So I think the next steps for monitoring is I would love to see more localized monitoring around airports. I think that that's a really great first step, but also understanding the complexity of the emissions that are coming out of them, that these lower cost technologies might not be able to answer. So being open to like a more iterative process, which I know can be challenging when you've been facing these challenges for a long time. But I guess that's, as somebody who works with orgs who are interested in airport emissions, we know based on, the emissions profile that our monitors might not be able to get them the answers that they need. So just, kind of being aware of that and being open to the educational piece of it.
Sure. I actually think the idea of also focusing on the solution side with communities as well, especially given the discussions in the noise meetings and presentations. While there was debate about whether or not some of the noise abatements can be effective or not, we actually know quite a bit about indoor-outdoor air quality movement, even with NIOSH and other groups understand in ambient to indoor environments. So sealed buildings, clean building technology can help. It doesn't always improve, obviously, the ambient exposure, but communities work on that. And I think coming back to the cafe example, you have the hyperlink in there. That's actually where that study has gone in when it comes to roads, is now teaming up with HUD to identify build-in solutions to reduce the indoor. And there's a lot that we can learn from the roadway work here with ultrafine particle health, as well as solutions that they're trying to build towards that could maybe help jumpstart that when we're thinking about aviation as well.
Well, I want to thank all our presenters and my co-chair, Eric Liu, as well, and thank you for your rapt attention.